Okay, so good evening. I'm Calvin Paul Joseph, and today I'll be conducting the week 5 problem solving and doubt clearing session for the course Electrical Measurements and Electronic Instrumentation, so which was taught by Professor Sheikh Chatterjee of IIT Kharagpur. Okay, so today what we will touch upon is what is a practical inductor. Okay, yes, Many, your voice is not coming. Okay, yes, is it audible now? Okay, great. Thank you. Okay, so we will be considering what is a practical inductor. Okay, great. So now we will be considering what is a practical inductor, what is a practical capacitor, and how the goal of the course is we want to measure. We want to take proper measurements of them. So then we have to use something known as an AC bridge. An AC bridge can be used to measure these values of the practical inductor, practical capacitor. And why do we use bridges? Because they provide us the flexibility of varying certain quantities such that we can get an estimate of the actual inductance or capacitor or its parasitic resistance, etc. Okay. And then we also need to find something known as a balance condition. At balance condition, then we can say we can use that to find the value of these inductor capacitors. And then we will solve some example sums. Okay. So if you have any doubts, you can unmute and you can ask them. If you have any queries, you can stop me. Or if you're not able to unmute and talk, you can send your questions in the chat. All right. So now we will start with week 5. So we will consider what is a inductor. Okay. So this is an inductor. This is the current which is flowing through it. This is the voltage across the inductor, and this is the inductance L. So we know that this is given by L di by dt. The voltage across the inductor is dependent on the rate of change of current across the inductor. Sorry. Also, in case it was an AC quantity, and there's a sine wave of frequency omega, then we have V is equal to I into J omega L. Okay, and that impedance is actually given by J omega L. Right? So this is for an ideal inductor. But in a practical inductor, there will be certain resistance. So a practical inductor is represented by a part where it is an ideal inductor and some actual practical resistance which comes. Okay. So you cannot have any practical resistance, you cannot have any ideal resistance, you cannot have any ideal inductor. So when the inductor is made, there are certain, it is wound. Okay, it is turns are there, etc. There is certain wire is there, and in that wire there will be some resistance. So that resistance comes in part. So an inductor is has certain resistance in series. Okay. So now if we find a difference equation or the differential equation, V of t is given by Ls di of t of dt plus Rs into I of t. Okay. Sorry. And that impedance Z is given by j omega Ls plus Rs. Any doubts still here? Okay. So this is the impedance Z for a practical inductor. Now let us consider for a capacitor. Suppose this is my capacitor C. There's a voltage of V of t and current which flows is I of t. So what is the relation? We know I of t is equal to C into dV of t upon dt. But, and the impedance of a practical of the capacitor is given by Z is equal to 1 upon j omega C. Or it can be written as minus 1 upon j omega C, right? But let us consider case of a practical capacitor. In an ideal inductor, what will happen? There will be no current which will flow through this dielectric. But in a practical capacitor, there will be some current which will flow. So that is given by what is known as our, like some parasitic leakage current will flow. And this is your capacitor, right? This is your current, this is your voltage. So now my I of t is given by Cp into dV of t upon dt plus V of t upon Rp. And the impedance is given by the combination of Cp and Rp. So my impedance Z is given by, Rp, which is parallel to 1 upon j omega C, j omega Cp. So this is my impedance Z. A better way to represent it is in terms of admittance. In terms of admittance, because they are in parallel, admittance makes it simpler. So Y is actually equal to 1 upon Rp plus j omega Cp. So this is the admittance of a practical capacitor. All right.
Okay, sir.
Any questions? Any questions still now? Okay.
इम्पीडेंस को रिएक्टेंस बोल सकते हैं सर यहाँ पे?
नहीं, अगर रेसिस्टेंस आ जाते हैं तो इम्पीडेंस बोलना पड़ता है. सिर्फ जो इमेजिनरी पार्ट है उसको रिएक्टेंस बता सकते हैं.
अच्छा, मींस प्योर इंडक्टर और कैपेसिटर रहेगा या कंबाइंड रहेगा तो उसको रिएक्टेंस बोलेंगे?
देखो, प्योर इंडक्टर रहेगा तो वो रिएक्टेंस हो जाते हैं, और प्रैक्टिकल इंडक्टर में जो ये पार्ट है ना वो रिएक्टेंस है.
ओके सर.
और जो कंप्लीट पार्ट है वो हुआ आपका इम्पीडेंस.
राइट सर.
ठीक है. सो नाउ
ओके सर.
we will consider for a practical inductor. We already saw that the Z is given by a series resistance plus some inductance. Now, how good is this inductor is denoted using something known as the Q, which is given by the quality factor. So if you want the inductance to be very, very good, we want the inductance to be good. What we want is this quantity to be very high, this quantity to be low. So we write omega Ls in the numerator and Rs in the denominator. So if Ls increases, then my quality factor will increase, and then I'll say that my inductor is very close to ideal. If my Rs increases, what will happen? My Q will reduce. And then we'll say that my inductor ideality is low. Okay, the quality of the inductor is not good. But if my RS reduces, then my quality factor will increase. Okay. So this is Q is known as a quality factor, which is equal to omega Ls upon Rs. Similarly, for a capacitor, it is Cp and Rp, right? So what do we want? We want my Rp to be as high as possible. Okay, if my Rp is as high as possible, then less current will flow. Then this I leakage will be less. If my Rp is very high, my I leakage will be less. That is what we want. And also you want Cp to be very high. So for capacitors, we use something known as dissipation factor, which is known as the badness factor. So that is given by 1 upon Rp omega Cp. Okay, we want my Rp to be as high as possible. We want my Cp also to be as high as possible. Then we say that a capacitor is quite close to behave like an ideal capacitor. Okay. Any doubts in this? Yeah. So now we will consider AC bridges. So now we know what is a practical inductor, practical capacitor, and now we want to we want to measure the impedance. The impedance measurement means what? Like we want to find both the RS and LS for a practical inductor. We want to find both the RP and CP for a practical capacitor, etc. Right? So we have a bridge and we have a voltage source. So this is, let us say this is my Z1. Okay. This is the galvanometer. This is my Z2. This is Z3. And this is Z4. So this is assumed to be a sine wave source. Sine wave source. So we want to find what is the balance condition. So at the balance condition, what you must remember is you must multiply the opposite end. So you must multiply this and this and this and this, and they must be equal. So you want Z1 into Z4 to be equal to Z2 into Z3. So earlier you were studying how to measure resistance using bridges, etc. You even studied Kelvin's double bridge, etc. So for resistance, it is simpler because it is only magnitude. But when you come to impedance, it is more complex. It has a real part, imaginary part, etc. So let us say my Z1 is a practical inductor. So it has a RS plus J omega LS, right? So now what we need, what is the magnitude of Z1? That is the square root of RS square plus omega LS square. What is the angle of Z1? The angle of Z1 is the tan inverse of the imaginary part, that is omega LS upon RS. Okay. So Z1 can also be written as magnitude of Z1 and angle of Z1. Now, for balance condition, there are two things that has to be satisfied. Magnitude and phase. Both should be satisfied. What does that mean? Magnitude means mod of Z1 into mod of Z4 to be equal to mod of Z2 into mod of Z3. What does phase mean? Angle of Z1 plus angle of Z4 should be equal to angle of Z2 plus angle of Z3. Okay. So only if both these conditions, if this condition A and this condition B, only if both are satisfied, then only we can say that the bridge is balanced. Okay. Only if both these conditions are satisfied, then only we can say the bridge is balanced. Otherwise, the bridge is not balanced. And we cannot get zero deflection. So this makes it little bit more difficult for us. How do we design bridges, etc., which will satisfy this balance condition? Now, let us see for this inductor, what will be the, like we know that my Z1, my magnitude is RS square plus omega LS square. What is the range of Z1? Range of angle of Z1? Can anyone tell me? Niranjan and Yasmini. What is the range of angle of Z1? How much can Z1 be? The angle of Z1 be?
$90, sir. 0 to 90 degree.
0 to 90 degree. Correct. So how do we get that? So
सर
if
एक
my
मिनट सर ये
uh,
एंगल सर कैसे लाए सर यहाँ पर tan इनवर्स WL/LS by RS.
हाँ, तो ये जो Z1 है, जो RS प्लस जे ओमेगा LS है, ये RS क्या है? रियल पार्ट है, और ये ओमेगा LS
ठीक,
क्या है?
ओके
उसका
सर.
इमेजिनरी पार्ट है. ठीक है.
ओके सर.
तो वो एंगल होता है वो tan इनवर्स ऑफ इमेजिनरी पार्ट बाय रियल पार्ट.
यस सर.
उससे आते हैं. जैसे मैग्नीट्यूड क्या होता है? रियल पार्ट का स्क्वायर प्लस इमेजिनरी पार्ट का स्क्वायर. वैसे
राइट सर,
एंगल
राइट.
होता है tan इनवर्स ऑफ इमेजिनरी पार्ट अपॉन रियल पार्ट.
L/B हुआ क्या सर?
सॉरी,
L/B हुआ क्या सर?
L बाई बी नहीं. L बाई बी मतलब
tan थीटा इक्वल टू L/B होता है ना सर.
लेंथ
राइट
अपॉन.
एंगल
अच्छा
ट्रायंगल
अच्छा
बना.
अच्छा, आप ऐसा बोल रहे हैं. ठीक है, बता दूँ. तो आपका जो इम्पिडेंस जो Z है ना, वो
यस
आपका
सर.
RS RS है और ओमेगा LS है. ओमेगा
यस
LS और RS परपेंडिकुलर है. तो ये होता है आपका एंगल. वो एंगल
सर.
आपका
राइट सर.
ऑपोजिट अपॉन एडजेसेंट हुआ. इसलिए बोलते हैं tan
यस
थीटा
सर.
इज इक्वल टू ओमेगा LS अपॉन RS. हाँ. तो आपका
यस
ये
राइट
क्या है
सर।
आपका इमेजिनरी पार्ट और ये आपका रियल
हम्म।
पार्ट हुआ। तो आपका
यस
थीटा इज
सर।
इक्वल टू tan इनवर्स ऑफ इमेजिनरी पार्ट अपॉन रियल पार्ट। ठीक है।
सर और एक डाउट था, मान
हाँ हाँ।
लीजिए ये पैरेलल में रहेगा तो फिर इसका एंगल सेम रहेगा या अलग होगा?
पैरेलल में है। अच्छा एक मिनट, पैरेलल के लिए सो व्हेन इट इज पैरेलल दिस LP अपॉन RP। हाँ
यस सर।
हाँ, तो भी वो सेम रहना चाहिए क्योंकि आपका, आप एक बात याद रखना चाहिए, आपका LP इज नॉट इक्वल टू LS, आपका RP इज
यस
नॉट
सर।
इक्वल टू RS। उसका एक कंडीशन है, उसको
यस सर।
डिराइव करके आपको LP इन टर्म्स ऑफ LS एंड RS मिलेगा और RP इन टर्म्स ऑफ RS एंड LS मिलेगा। ठीक है। पर अभी अगर
यस।
इसका एंगल ढूंढना है, इसका एंगल ढूंढना है, तो आपका क्या करना पड़ेगा, आपका Z क्या है, RP पैरेलल टू J ओमेगा LP, ये हो गया। तो आपका Z हुआ RP इंटू J ओमेगा
जे ओमेगा
LP
एल
अपॉन RP
प्लस
प्लस J
प्लस।
ओमेगा LP। सो इन दिस आपका डिनोमिनेटर में इमेजिनरी टर्म है, तो ये थोड़ा कॉम्प्लिकेटेड
इसको
बनाता है।
हटाना पड़ेगा।
तो
यस सर,
इसका क्या करते
ऊपर
हैं,
उठाना पड़ेगा उसको।
हाँ ऊपर उठाना पड़ेगा, तो ऊपर जब भी उठाते हैं
यस
इसका
यस सर।
कॉम्प्लेक्स कॉन्जुगेट से मल्टीप्लाई करते हैं। तो
यस
ये
यस
हुआ
सर।
RP J ओमेगा
हम्म।
LP इंटू
हम्म।
RP माइनस J ओमेगा LP, और
राइट सर।
डिनोमिनेटर में RP
आरपी
प्लस
माइनस।
J ओमेगा LP इंटू RP माइनस J ओमेगा LP।
यस
तो
सर।
आपका Z क्या हुआ, RP स्क्वायर J ओमेगा LP माइनस माइनस जे जे
प्लस हो
जे
जाएगा।
स्क्वायर, तो प्लस हुआ, तो प्लस
प्लस हो जाएगा।
RP ओमेगा स्क्वायर LP स्क्वायर अपॉन,
यस सर।
ये हुआ आपका RP
आरपी
स्क्वायर
स्क्वायर
प्लस ओमेगा
प्लस।
स्क्वायर LP स्क्वायर। तो
ठीक।
आपका Z हुआ आपका ओमेगा स्क्वायर LP स्क्वायर RP प्लस जे, अरे सॉरी, Z इक्वल टू RP ओमेगा स्क्वायर LP स्क्वायर प्लस J RP स्क्वायर ओमेगा LP अपॉन RP स्क्वायर प्लस ओमेगा स्क्वायर LP स्क्वायर। ठीक है।
ओके
तो
सर।
ये फिर आपका इमेजिनरी पार्ट क्या होता है,
अलग
आपका
करना
रियल
पड़ेगा।
पार्ट हुआ RP
हम्म।
ओमेगा स्क्वायर LP स्क्वायर अपॉन RP स्क्वायर प्लस ओमेगा स्क्वायर LP स्क्वायर। आपका इमेजिनरी पार्ट हुआ RP स्क्वायर ओमेगा LP अपॉन RP स्क्वायर प्लस ओमेगा स्क्वायर LP स्क्वायर। इस हिसाब से
यस।
अगर अभी आप tan थीटा निकालोगे, वो होगा आपका इमेजिनरी बाई रियल, वो हुआ
यस
आपका
सर।
RP स्क्वायर ओमेगा LP अपॉन RP इंटू
ओमेगा।
ओमेगा स्क्वायर LP स्क्वायर। डिनोमिनेटर कॉमन है, वो कट जाएगा, तो
यस सर।
वो
यस
हो
सर।
जाता है आपका RP अपॉन ओमेगा LP। ठीक है।
यस सर।
तो आपका थीटा हुआ tan इनवर्स ऑफ RP अपॉन ओमेगा LP। ओके।
यस सर।
तो यशविनी,
रिवर्स।
you're able to understand Hindi or you're fine with Hindi? हाँ। अब और अभी और कुछ पूछ रहे थे?
ठीक है सर।
ठीक है। ओके ओके तो so this is for this. So when you go to impedance, it is like a phasor, and phasor becomes complicated. There is magnitude and angle, both you have to consider. Okay. So now we studied about AC bridges, etc. Okay. So for a pure capacitor, What is the angle of Z here for a capacitor? For this capacitor, what is the angle of Z?
-90 degree negative, sir.
Minus 90 degree. And when resistance is added, what is the angle?
Leg by 90 degree, sir. Current leg by 90 degree.
It can range from 0 to minus 90 degree. The angle of
Yes.
Z, when there is a resistance and a capacitance, it can range from 0 to minus 90 degree. Now, I'll ask you a question. If I have a resistor R or an inductor L, I have a capacitor C. Okay. What will be the angle of this? What will be the angle of this Z?
0, sir. 0 degree.
0 degree. Why?
Both cancel out हो जाएगा, sir.
That doesn't happen always. So this is represented R j omega L, and this is 1 upon j omega C. So your Z
दोनों का
is
मैग्नीट्यूड सेम रहेगा तो कैंसिल आउट हो जाएगा ना, सर.
अगर सेम रहेगा तो हर बार सेम नहीं होता है
यस
ना.
सर. तो फिर
So
फेजर सम
it
होगा,
is
सर. फिर
ये R plus j omega L minus 1 upon omega C. So if my so there are three conditions. Condition A, when omega L is equal to 1 upon omega C. Then what happens is your circuit is in resonance. And your Z is just equal to R. And your angle of Z is how much then?
0, sir.
Your angle of Z is just 0 degree in this case. But now, assume omega L is greater than 1 upon omega C. Then what will be your angle of Z?
0 between 0 to 90 degree, sir.
Yes, it will be between 0 to 90 degree. Because in this case, though there is a capacitance and there's an inductance, the circuit will behave in an inductive manner because your inductance is dominating over your capacitance. So that's why your angle can range between 0 to 90 degree. But in the case when omega L is less than omega C, then what will be the angle of Z?
Between 0 to minus 90 degree, sir.
Now it will range between 0 to minus 90 degree because now it is a capacitive behavior. The capacitance is dominating. In this case, it is an inductive behavior. Okay. So, any queries, any doubts till now?
No, sir.
Okay. So, if there are no doubts, we will start solving questions. Start. Okay. So this is the question. Okay. What are they asking? We want to find the angular frequency. Okay. R4 by R3. Uh, so this is the bridge. So they are told we want to find what is the angular frequency. So what is Z1 over here?
L1 parallel R1 sir.
Okay. So Z1 is R1 parallel to J omega L1. So first, let us see this circuit, this bridge. There is this Z1. You have Z2. So Z1 and Z2 both are a combination of resistance and inductance. Then you have Z3. Then you have Z4. Now, we want at balance condition, what will happen? Z1 into what? Z1 into what?
Z4 sir.
Z1 into Z4 is equal to Z2 into Z3. If you notice, Z4 and Z3 both are resistors. So we can write Z1 is equal to Z3 upon Z4 into Z2. So that is written as Z1 is equal to Z3 is what? R3 upon R4 into Z2. So this is known as, this is no, now you see R3 upon R4, it is purely real. And this is known as a ratio bridge. Okay, this is, such bridges are a little bit more simpler to find the balance condition and all. Okay. So now, what is your Z1? Can you calculate and tell me? Like I want it in terms as an
Yes sir.
expression of R1 and L1. Okay, I don't want the values. I want it
Yes
in
sir.
terms of
R1 into J omega LP by R1 plus J omega LP.
So this is my Z1. So your Z1 is R1 into J omega L1 upon R1 plus J omega L1. What is the Z2?
R2 plus J omega L.
So Z2 is equal to R2 plus J omega
J omega
L2.
L.
We know my Z1 is equal to R3 upon R4 into Z2. So my Z1 is R1 J omega L1 upon R1 plus J omega L1 is equal to R3 upon R4 into R2 plus J omega L2. Now what should we do?
अब कम रियल और इमेजिनरी पार्ट को कंपेयर करेंगे
Now how can we do that?
इसका जो नीचे पे जे टर्म है उसको पहले हटाएंगे सर लेफ्ट साइड को
अच्छा तो वो कैसा करना है?
फिर उसके बाद R1 माइनस जे ओमेगा L1 को ऊपर नीचे ये करेंगे सर नोमिनेटर
अच्छा
डिनोमिनेटर से
ओके वो भी कर सकते हैं। ये दूसरा बात है कि ये यहाँ पे भी मल्टीप्लाई कर सकते हैं ना, वो भी कर सकते हैं।
हाँ वो भी हो सकता है ठीक ठीक है सर वो भी हो सकता है
तो हम लोग क्या करते हैं R1 J omega L1 is equal to R3 upon R4 into R2 plus J omega L2 into R1 plus J omega L1। ठीक है, ये क्या होता है? मल्टीप्लाई करके बोलो क्या होता है?
R1 into R2 प्लस J ब्रैकेट में रहेगा सर ओमेगा L1 R2
हाँ
प्लस J ओमेगा L2 R1
हाँ
माइनस ओमेगा स्क्वायर L1 L2।
अच्छा ठीक है। अभी जे ओमेगा R1 L1 is equal to R3 upon R4 into R1 R2 minus omega square L1 L2 plus J into
J ओमेगा L1
omega L1 R2 minus omega plus omega L2 R1. Okay.
राइट सर।
So now what should we do?
कंपेयर करें सर रियल टर्म को रियल से और इमेजिनरी को इमेजिनरी से।
So we must equate the real and imaginary terms. So what do we get then?
रियल तो जीरो है सर।
So 0 is equal to
R3/R4 into R1 R2 minus omega square L1 L2।
and imaginary term. What do we get?
R1 L2 R1 L1 equal to omega square sorry omega L1 R2 plus omega L2 R1।
Yeah, so omega R1 L1 is equal to omega L1 R2 plus L2 R1.
राइट सर।
So omega and omega get cancelled. So we get R1 L1 is equal to L1 R2 plus L2 R1. Right? So now this R3 upon R4 is common. So they will go away. So we have R1 into R2 minus omega square L1 into L2. So now what is my omega?
अंडर रूट में आ जाएगा सर।
Yeah.
1 by R1 R1 R2 by L1 L2।
तो आपका ओमेगा हुआ R1 R2 बाई L1 L2। ठीक है। तो आपका R1 कितना है? R1 आपका 20 ओम है, आपका R2 10 ओम है और L1 L2 दोनों 150 मिली एम्पियर। तो ये R1 इक्वल टू 20 ओम, R2 इज इक्वल टू 10 ओम, L1 इज इक्वल टू L2 इज इक्वल टू 150 मिली हेनरी। तो व्हाट इज द ओमेगा? व्हाट इज ओमेगा?
डबल 154.70।
मतलब
उतना ही होना चाहिए। 1154 सर 0.70। 70 है।
70।
यस सर।
पक्का?
एक मिनट सर। वेट वेट सर। 94.28 है सर।
हाँ एक्चुअली
रेडियन पर सेकंड है ना सर।
हाँ okay 94.28 radians per second. So now we found omega. Next they are telling us to find, we have to find R4 upon R3. How much is R4 upon R3? Okay. So we have to
Z2
find
by Z1 सर।
R4 upon R3. So we have made a mistake. When we were equating imaginary part, we forgot to consider this. This we forgot to consider. So this we have to find out. So when we are equating the imaginary part, what do we get? Omega R1 L1. Omega R1 L1 is equal to R3 upon R4 into omega L1 R2 plus omega L2 R2. Omega L1 R2 plus L2 into R1. Right? So now what will happen? Omega will get cancelled. So we have R1 L1 upon L1 R2 plus L2 R1 is equal to R3 upon R4. But what do we want? We want
R4 by
R4
R3
by R3. So that is equal to L1 R2 plus L2 R1 upon R1 into L1. So that becomes equal to my R2 upon R1 plus L2 upon L1. So how much is that? So what is R2? My R2 is 10 and my R1 is 20 and my L1 is 2 is 150 millihenry, L1 is 150 millihenry. So how much is this?
.5 सर।
How much?
0.5
Okay. So this actually
0.5
is
1.2 सर। 1.2 होगा।
no. This is 0.5 plus 1. So this
1.2
actually is equal to
1.5 sorry sir।
1.5.
1.5
So it is 1.5.
15 by 10 15 by 10
हाँ 15 by 10.
3/2 हो जाएगा तब तक। 3/2
वो 1.5. So any doubts still here?
नो सर।
अच्छा. So when do you submit your assignments?
नहीं किए सर, लेकिन बना लिए थे इससे पहले।
मतलब
और एक मतलब क्लास हुआ था ना सर, उससे हम बना लिए थे।
हाँ. अच्छा.
सबमिट नहीं किए सर।
अभी आप कौन सा असाइनमेंट सबमिट करोगे?
5th सर।
अभी आप असाइनमेंट फाइल सबमिट करोगे?
यस सर।
अच्छा.
वीक 5 का सर।
ओके. अभी आप सबमिट करोगे मतलब ये वेडनेसडे को आप सबमिट
28 तक करना है सर।
28. हाँ
ड्यू डेट 28 तारीख को।
28 12 बजे कि 5 बजे?
12 तक है सर।
ओके. ठीक है। और आपने
सर एक
हम पूछो, बोलो।
जो सर एग्जाम होगा सर, फाइनल होगा, उसमें इसी टाइप का क्वेश्चन आएगा कि अलग टाइप का आएगा सर?
हाँ, इसी टाइप का आएगा। हाँ। और आप 2-3
केवल
NPTEL का एग्जाम्स दे रहे हैं ना?
2 पेपर का सर?
अच्छा अच्छा। हाँ, और आप कुछ और पूछ रहे थे?
क्या सर?
आप और कुछ पूछ रहे थे?
बस यही सर, यही जानना था कि क्वेश्चन किस टाइप का आएगा उसमें फाइनल वाला में।
दो टाइप कर रहे थे, एक MCQ, एक है न्यूमेरिक आंसर टाइप। तो ये न्यूमेरिक आंसर टाइप का क्वेश्चन है। हम्म।
सब ऑब्जेक्टिव रहेगा क्या सर?
हाँ, ऑब्जेक्टिव रहेगा, मतलब आपको सिर्फ आंसर डालना है, आपको स्टेप्स दिखाना नहीं पड़ता है।
अच्छा।
जैसे कैसा
जैसे
हमारा।
सर
हाँ
जैसे एनालॉग इलेक्ट्रॉनिक्स में जैसे सर ऑप्शन बेसिस से अभी असाइनमेंट जो क्वेश्चन है वो
हाँ
ये ऑब्जेक्टिव मतलब 4 ऑप्शन बेसिस है, तो
हाँ।
जैसे मेजरमेंट में ऑप्शन बेसिस से नहीं है, तो मतलब दोनों में क्या अलग रहेगा कि एक ही जैसा रहेगा?
नहीं, मतलब मेजरमेंट्स में थोड़ा कम ऑब्जेक्टिव बेस्ड क्वेश्चन से है। अ, पर 1 2 3 आना चाहिए वैसे। मेनली आपका न्यूमेरिक आंसर टाइप आएगा, क्योंकि इसमें बहुत सारा सम्स है। तो सॉल्व करके एक न्यूमेरिक
यस सर।
आंसर वैल्यू चाहिए। और
ओके।
जैसे ये एग्जांपल ले लो, यहाँ पे आंसर है 1.5। ऐसा नहीं आना चाहिए
यस
कि
सर।
आपको सिर्फ 1.5 आंसर दोगे फिर ही राइट। अगर
यस सर।
आपने 1.48 लिखा तो भी चलेगा, तो भी ये राइट है। आपने
ओके।
1.53 लिखा तो भी राइट है, क्योंकि
मीन्स
लोग
नियर वैल्यू होना चाहिए सर?
हाँ, नियर वैल्यू होना चाहिए बस। इसमें बहुत
ओके
एक्यूरेट
सर।
आएगा 1.5। बाकी इसमें क्या होता है, फ्रैक्शन जैसा आता है। तो फ्रैक्शन में होगा तो कितना एक्यूरेसी आप तो मालूम नहीं उन लोगों को कितना चाहिए, आपको कितना चाहिए। तो नियर अप्रोक्सीमेट वैल्यू देना पड़ता है।
ओके सर।
ये कोई लोग ने पूछा, given any arbitrary set of fixed values of L1, L2, R1, R2, R3, and R4, it is always possible to obtain a balance by adjusting only the frequency of the supply. Is this true or false? ये क्या सच है कि गलत है?
होगा, फॉल्स तो होगा सर, लेकिन लॉजिक इसका
फॉल्स होगा, पर क्यों? ठीक है। So the question says is that given any arbitrary set of fixed values, so L1 is some value, L2 is some value, R1 is some value, R2 is value, R3 and R4 also there's some value. So now they're saying, is it possible to obtain a balance? So they want it to be balanced. But for balance condition, what is that? There's a real part and there is an imaginary part. Okay. They are saying the only thing we can change is the frequency. Only thing we can change is the frequency. So in the real part, what do we have? This is the expression for real part. So here somehow you can may think that at some particular frequency, this can be true, this can be valid because you're changing omega. Omega you can change. But for the imaginary part, the expression is given like this. Here, omega is not present. Omega is not available. Okay. So even if you change omega, in case they were not balanced earlier, it will not get balanced later also. Because omega only you can change, but that will not affect the imaginary part of your equation. Your balance condition will not be fulfilled. Okay. And hence you cannot achieve a balance. So any doubts?
मीन सर पॉसिबल है लेकिन ऑलवेज पॉसिबल नहीं है क्या सर?
नहीं, उन लोग ने क्या बोला कि R1 फिक्स्ड है, R2 फिक्स्ड है, R3 फिक्स्ड है, R4 फिक्स्ड है, L1 फिक्स्ड है, L2 फिक्स्ड है। सिर्फ ओमेगा चेंज हो सकते हैं, ओनली ओमेगा यू कैन चेंज। तो बाई चांस क्या हुआ आपका R1 L1 अपॉन जो भी योर R1 L1 अपॉन L1 R2 प्लस R2 R1 कोई फिक्स वैल्यू से इसका वैल्यू हुआ बाई चांस आपका 30 हुआ, समझ लो।
यस यस सर।
और आपका R3 पे R4 हुआ 20, तो बैलेंस कर ही नहीं पाओगे आप, क्योंकि इधर ये सब फिक्स्ड है, सिर्फ ओमेगा चेंज कर सकते हैं। तो आपका क्या होता है R1 L1 अपॉन L1 R2 प्लस L2 R1 is not equal to R3 upon R4. So then balance condition is not possible.
राइट सर।
इसलिए हम लोग को बाकी चीजों में भी चेंज करने का ऑप्शन देना चाहिए। Now, so now these are the YouTube links and Drive link. I'll post in the chat. So the Drive link will have these lecture notes. So the lecture notes will be made into a PDF and it will be uploaded on the Drive. So you can access these notes later as well. The YouTube link is the link to my channel where I will upload this video later. Okay. So that you can check these things. So you can access these lecture and these notes. Now, what we'll do, we'll go to the next question. So they are asking, this bridge can be balanced if the supply waveform is A sinusoidal, B square, C triangular, D is it any periodic function, E is it any half wave symmetric function. Okay. So they are asking us to balance the bridge. Can we balance the bridge? If my supply waveform is sinusoidal, so how is the sinusoidal wave given? like this. How is a square wave shown? Like this. Okay, so this is a square wave. How is a triangular wave? Like this. Okay. So can the bridge be balanced if the supply waveform is sinusoidal or square or triangular, any periodic function or any half symmetric function? Can anyone tell me when will it be balanced? For which condition? Hmm? So Niranjan and Yasmini, have you heard about Fourier series? A. So why only for sinusoid? Why it cannot be balanced for square wave or triangular wave? Like what is so special in the sine wave that it is getting balanced only for sine wave? It is not getting balanced for square wave and triangular wave. What is the reason? Okay, have you both heard of Fourier series? Hmm? Yes, Yasmini and Niranjan?
Yes.
Yes. Okay. So what do you mean by Fourier series? Fourier series means it takes any periodic signal which will satisfy certain conditions, such as something known as some like continuity or it should be integrable or it should be within limits, etc. There are many sort of constraints are there, but basically your signal is a periodic signal. So sine wave is periodic. We agree. Is a square wave periodic?
Yes, sir.
Okay. And my triangular wave is periodic. So now
Yes, sir.
it says let us assume I'm considering this square wave. Okay, square wave. It is a signal given by let us say some y of t. Okay. Now at and this is at some frequency. Let us say what is the frequency? Let us say frequency of it is 10 hertz. 10 hertz. Fourier was a scientist who made this. It's a very breakthrough kind of discovery that he said that any periodic wave from any periodic signal, I can write it in terms of sine waves. So this square wave, which is not in the shape of any sine wave, look, you see the square wave, it is so different from the sine wave. It has only one function similar, one probably similar to this sine wave, that it is periodic. Otherwise, it is so different from your sine wave. So he's told that my square wave can be represented by multiple sine waves. So what does he mean? So this square wave can be made from one sine wave like this over here plus another sine wave like this, right? And so on. And then I'll add another fifth harmonic. So that would be something like this, this and this. 2.5 plus 1, 2, something like this. Okay, it's not to the scale, but it is something similar. So what he's saying is, if I add multiple sine waves, I can effectively get my square wave. Okay, my drawing is not good, not that great, but you can get the understanding. Like I can represent a square wave using multiple sine waves. Okay, so my y of t actually is equal to some a sine of omega t plus some a3 sine of 3 omega t plus this a5 sine of 5 omega t plus dot dot dot. Okay, why only odd harmonics I'm considering is because of the property of the square wave. Okay, but what you can see is that my square wave can be decomposed into multiple sine waves. So now in the balance condition, suppose my balance condition is this is fixed. This is happening. I have R1 L1 upon L1 R2 plus L2 R1 is equal to R3 upon R4. This is, I have set R1 and R3 and everything I've set such that this is getting balanced. But the problem is where? The problem is in the real part. In the real part, what I want is R3 upon R4 into R1 R2 minus omega square L1 L2. So this omega, this will change. So the square wave of frequency 10 hertz has one omega at 10 hertz. It has another omega at 30 hertz. It has another omega at 50 hertz. And if you want it to be balanced, it should be valid for all frequencies, which is not possible. It can be valid only for one frequency. So it will not be able to reach a balance condition. Any, do you want me to repeat it again? Or you guys have understood? Okay. So first is we realize that it is a periodic signal. Yes. So it is a periodic signal. So we consider the example of a square wave. So the square wave, Fourier discovered that the square wave can be written in terms of multiple sine waves. In terms of, so there's the sine wave. So we have this sine wave. This is the first sine wave. This is the second sine wave. This is the third sine wave. And there will be more and more. It will be like an infinite series. More and more sine waves we add, more and more accurate square wave we will get. So the square wave is in actual reality made up of multiple sine waves or different amplitude, different phase, etc. Okay. So now this equation can get balanced by R1, L1, R3, R4 because it does not depend on the frequency. But this equation depends on the frequency. And because this equation can be satisfied, we found that it can be satisfied at only 1 omega. There will be only one unique, sorry, there will be only one unique omega, only one, at which this can be satisfied. It cannot be satisfied for 10 hertz and 30 hertz and 50 hertz. That is not possible. You can get satisfied at only 1 omega. So it might be satisfied for 1 omega, but for the other omegas, it is not getting satisfied. If it is not getting satisfied for other frequencies, then we cannot say that the bridge is balanced. Then there will be some current in this galvanometer. There will be some current when it is not balanced. Hence, we always use a sine wave. We cannot use a square wave. We cannot use a triangular wave. We cannot use any other wave. Okay? Is it clear?
ओके सर, वो साइन वेव रहता था सर, उसमें दिक्कत था।
हाँ, सिर्फ साइन वेव से होगा, क्योंकि दूसरा पीरियोडिक वेव्स में बहुत सारा साइन वेव्स रहते हैं अलग अलग फ्रीक्वेंसी से, तो वो हर एक साइन वेव को बैलेंस आउट नहीं कर पाएंगे। So so this is this question. So this is actually Schering bridge. So can anyone tell me what is the use of this bridge? Why do we use this? Achha. This bridge is used because for measuring high voltage capacitors. So I want to find Cx and Rx. Now this capacitor is rated for very high voltage, for some high voltage, say 500 volt something. It is rated for 500 volt. Now if I test that capacitance at 10 volt, I may get its value to be 1 microfarad. If I test it at say 300 volt, I will get its value to be, let us say, 0.8 microfarad. If I test it at 500 volt, I will get its value to be around 0.75 microfarads. Okay. So at different voltages, the capacitance you will observe is different. And that happens. So what we want to do is add the voltage in which we will be using it. We want to find the capacitance at that voltage. Okay. So this is like, it derates. As the voltage increases, the effective capacitance will reduce. So what we want to do is, I have a capacitor. I want to find that capacitance at the voltage in which I will be using that circuit. So for that, if it's a high voltage capacitor, I must apply a high voltage to be able to find its capacitance at that high voltage at which it will be used. Okay. So this is my capacitance. So now can you find the balance condition of the Schering bridge? This is a Schering bridge. Okay. What is the balance condition for this? So first of all, is this a ratio bridge or a product bridge? No, Z1 into Z. We have to do the product of these two. Okay, here there's no Z4, Z1 like that. We have 1 upon j omega C1 into R3 is equal to this 1 upon j omega Cx plus Rx into the Z2. Okay, this is your Z2. Let us say this is your Zx. Oh, you guys can hear? Can't hear? Just 1 minute. Let me switch off the fan. So now is it better? Okay, Yasmini, actually getting the video today would be a bit difficult because I have to merge and all that. It takes lots of time. So by tomorrow morning, hopefully it will get uploaded. Okay. So by the way, like, why are you facing network issues? Like, you're traveling or what? Acha, acha. So you're studying somewhere, or you're a BTech student, or you're preparing for GATE, or like what you're doing, or you're in which college? Okay, okay, BTech student. Okay. So now we want to find the balance condition. So what do we have to do? So it is 1 upon j omega cx plus rx into z2. In this case, as it is a product bridge. Why is it a product bridge? Because the multiplication of this is purely imaginary. It is not like some real part and imaginary part. It is purely imaginary. So it becomes easier. So what I do instead is I write it as R3 upon j omega C1. And this Z2, when I bring it here, I will write the admittance of Y2. Okay, the admittance of Y2. That is equal to 1 upon j omega Cx plus Rx. Right? So what will be the admittance of Y2? So that will be R3 upon j omega C1. What is Y2? That is equal to 1 by R2 plus j omega C2. This is equal to 1 upon j omega Cx plus Rx. Right? So now what do we get? R3 upon R2 into j omega C1 plus R3 into C2 upon C1 is equal to 1 upon j omega Cx plus Rx. So what we must do? We must equate the real and imaginary parts. So what do we get? We get R3 upon R2 omega C1 is equal to 1 upon omega Cx for the imaginary part, and for the real part, R3 into C2 upon C1 is equal to Rx. So we get omega omega get cancelled. So Cx is equal to C1 into R2 upon R3, and Rx is equal to C2 upon C1 into R3. Okay, so now we got the expressions for Cx and Rx. So now what we will do, you go to the question. They told C1 is 1 microfarad, C2 is 900 nanofarad. So we'll write down. So these are the values. So what will be Cx? Can you calculate and tell me? Hello. Even Rx. You have calculator? So this is actually 1 microfarad into R2 is 170 divided by R3, that is 0.3 kilo, that is 400. That actually becomes equal to 0.425 into 10 to the power minus 6, not 0.4. Okay, so it becomes 0.425 microfarad. Similarly, Rx, okay, so you find Rx, how much is Rx? So what is Rx? Yeah, Rx is 360 ohm. Okay, so we found Cx, we found Rx. Now what they're saying? They're saying the supply frequency is 60 hertz. Then you must estimate the dissipation D factor of the unknown capacitor. Okay, so they're saying frequency is 60 hertz. Now we have to find the dissipation factor. So the capacitor which we have is like this, Cx, Rx. We have to find the dissipation factor. But what do we know? That if it is like this, if it is Cp and Rp like this, then my dissipation factor is given by 1 upon omega Cp into Rp. But if it is in this like this, then how do you find the dissipation factor? That is the question. So what we must do is we must find the equivalent of these two. Okay, we must find the equivalent of these two. So that means my Zx should be equal to Zp. So that means my Rx plus 1 upon j omega Cx should be equal to Rp into 1 upon j omega Cp upon Rp plus 1 upon j omega Cp. Right? Now, I have this Rx j omega Cx plus 1 upon j omega Cx is equal to Rp upon 1 plus j omega Cp into Rp. Right? So now, what should I do? Let us assume I leave this like as it is. Assume I leave it as this formula. That is Rx plus 1 upon j omega Cx. So then I have to do the complex conjugate over here. So that is equal to Rp into 1 minus j omega Cp Rp upon 1 plus j omega Cp Rp into 1 minus j omega Cp Rp. So my Rx plus 1 upon j omega Cx is equal to Rp into 1 minus j omega Cp into Rp upon 1 plus omega square Cp square Rp square. So I get my Rx plus 1 upon j omega Cx is equal to Rp minus j omega Cp into Rp square upon 1 plus omega square Cp square Rp square. So now what do I know? So this I can write it as Rx minus J upon omega Cx is equal to Rp upon 1 plus omega square Cp square Rp square minus J omega Cp into Rp square 1 plus omega square Cp square into Rp square. Right? Any problems still here? So now we write Rx is equal to Rp and 1 plus omega square Cp square Rp square, and my 1 upon omega Cx is equal to C omega Cp Rp square upon 1 plus omega square Cp square into Rp square. Now if you look carefully, what you can do is you write 1 upon omega Cx is equal to omega Cp into Rp into my Rp upon 1 plus omega square Cp square Rp square. Right? Now what is Rp upon 1 plus omega square Cp square Rp square? That is equal to my Rx. So I have 1 upon omega Cx is equal to omega Cp into Rp into my Rx. Right? So what I have further, I have 1 upon omega Cx into Rx is equal to omega Cp into Rp. Now what is my dissipation factor? My dissipation factor is actually 1 upon omega Cp into Rp. And that actually is equal to omega Cx into Rx. And I know Cx, Rx, I know omega. So my dissipation factor is equal to 2 into pi into 60 into Cx. What is my Cx? Cx actually is 0.425 microfarad. And my Rx is 360. So can you calculate and tell me what is my dissipation factor?
Zero 0.57.
So it is
0.57.
0.7. Okay. So this is how step by step I saw.
0.057, sir.
So
0.057.
0.057. So these are
Yes.
step by step we solve. So it is not required you should remember all the formulas, right? I knew one formula that this is my dissipation factor. What is this? Oh, okay. So I knew one formula. I knew this formula. But then I did not find it in terms of that. So I had to convert it into CA. I had to find an equivalence. And then I found a new formula. I found out this formula. Right? So basically, you must
Yes.
understand the concept. You know the one formula, and then if you want to apply something similar, you can derive the required formula.
Okay, sir.
Okay. So now we'll go to the next question. Actually, they've asked something else also. If the supply voltage to the bridge is 4 kilovolt at a frequency of 60 hertz, then estimate the voltage across the variable or controllable arms in V at balance. So they are telling to find the voltage over here. Let me just So this is basically for high voltage, right? We want to find, so the voltage across CX, RX will be high. It will be high. But we want this voltage to be low. Why do we want it to be low? Because there will be some human or there will be some operator who will, what will he be doing? He will be changing R3, he'll be changing C2, he'll be changing R2. So we want that voltage V to be low for safety purpose. Okay, so that is the beauty of this bridge. This voltage can be high, but this voltage has to be low. So we want to find a balance condition. In balance condition, what happens? What happens is current is zero.
So it will be 0.
Current is zero. So whatever voltage which is applied over here, 4 kilovolt at frequency 60 hertz, it will get divided across this high and low. So this V low is actually equal to 4 kilovolt into 10 to the power 3 into what? This R3 upon R3 plus Rx plus 1 upon J omega Cx. So that actually
Okay.
V low is 4 into 10 to the power 3 into R3 upon square root of R3 plus Rx the whole square plus 1 upon omega Cx the whole square. Right?
कैसे किया सर ये मैग्नीट्यूड
Magnitude of R3, magnitude of R3 क्या हुआ? ये स्क्वायर ऑफ R3 स्क्वायर हुआ प्लस उसका इमेजिनरी पार्ट 0 है तो सीधा सीधा R3 हुआ और इसका रियल पार्ट और इमेजिनरी पार्ट का स्क्वायर. So that is equal to 4 into 10 to the power 3 into R3 upon square root of R3 plus Rx the whole square plus 1 upon omega Cx the whole square. So what is my R3? My R3 is 0.4 kilo ohm, that is 400 ohm. So this is equal to V low is 4 into 10 to the power 3 into 400 upon square root of 400 plus 360 square plus 1 upon 2 pi into 60 into Cx is 0.425 microfarad per square. So what is the answer of this?
टू 254.57.
Yes. So it comes out to be 254.57 volt. Okay. So this is also quite a high voltage, but the voltage across the capacitor which will be measured, this V high will be very high. It will be around like 3700 volt, around that. And this over here is around 254. Okay. So that's why this voltage is very high. This voltage is quite low. in comparison. That is the advantage of this configuration of this bridge network. So now we'll go to the next question. They're saying for a coil. So if you hear the term coil, you must understand it means an inductor. Okay, it means an inductor. And they're saying that power factor of the coil is 0.15. What does it mean? You have an inductor, it has a resistance and an inductance Ls, right? That impedance Z is actually R plus J omega Ls. They're saying the power factor is 0.15. So what is it? This is your R. This is your omega Ls. This is your Z. And this is your theta. So what is power factor in terms of theta?
Cos phi, cos theta.
So we know cos theta is equal to 0.15. So what is my theta?
Cos inverse 0.15.
So what is the value of that?
$81.37.
So theta is actually equal to 81.37 degree. Now, what is my quality factor in a coil?
Tan theta, no?
The quality factor is actually omega Ls by R, which is actually equal to your tan theta. So how much is it?
6.5.
So this 6.5912. Okay, don't just stop with 6.5. Try to go for more accuracy.
Yes. Yeah.
So we'll go to the next question. This is the question. So this is the question. So now at balance condition, what do we have? We have R1 into R3 is equal to this Z4 into Z2, right?
Yes, sir.
Now what do we know? What do we know? What don't we know? So now we want to find a balance condition. We can write it as R1 into R3 into Y4 is equal to Z2, right? Because it is preferred when your capacitance and resistors in series, the admittance is easier to find. Okay, and in inductor, the impedance is easier to find when it is in series. That's why I bring it in terms of admittance of your series RC and impedance of your series RL. So this makes it easy. Hmm. So this is R1 into R3, 1 upon R4 plus j omega C4. This is equal to your Z2. What is that? It is your R2 plus j omega L2. Okay, so I'll write down this point. Impedance of series RL and admittance of series RC are easier to find. Okay, so now what do I get? My R1 into R3 upon R4 is equal to R2, and my R1 into R3 into omega C4 is equal to omega L2. Omega omega get cancelled. And this is a for the resistors. My main concern is the capacitances, right? So what I get R1 into R3 into C4 is equal to L2. Till here, any doubts?
No, no, sir.
So now it puts us in a problem. No? We know the B factor of C4R4 is 0.16, and we want to find a quality factor of L2R. So what do? We know from here R1 into R3 is equal to R2 into R4. So I substitute that over here. So I get R2 into R4 into C4 is equal to L2. So then I can write it as R2 into R4 into omega C4 is equal to omega L2. So this further I can write it as omega C4 R4 is equal to omega L2 upon R2. So this is my quality factor of my inductor. And right? And this is my dissipation factor. Omega C4R4 is the dissipation factor, right?
Yes, sir.
Because it is in series. This series RC. So it comes like that. No. There's a mistake. There's a mistake. Mistake. So my dissipation factor is omega C4R4. And that they have given it to be 0.16. Right? Now we have to find a quality factor. So my quality factor actually is equal to my omega L2
1
upon
by
R2. Right? My inductance must be as high and my resistance must be as low. So my quality factor comes out to be omega L2 by R2, which is again omega C4 R4. Okay, which is 0.16. Okay, fine. Hmm. Is there any mistake in this? If you're able to find any mistake? Okay, so you can check this later. Hmm. Actually, there's a mistake. So the mistake is, first of all, this note is wrong. So your impedance of series RL is easy to find, but admittance of series RC, no, it should be admittance of parallel RC. So this part actually is wrong. Okay, this part actually is wrong. So what I will write is, I will write my R1 into R3 is equal to my Z2 into Z4. Okay, my R1 into R3 is equal to R2 plus J omega L2 into R4 plus 1 upon J omega C4. So it is R1 into R3 is equal to R2 into R4 plus J omega L2 R4 plus R2 upon J omega C4 plus L2 upon C4. Okay. So now, so these previous parts are all wrong. So let me cancel them. These are wrong. This also is wrong. Now, I will equate the real and imaginary parts. So what I get? R1 into R3 is equal to R2 into R4 plus L2 upon C4. And omega L2 R4 minus R2 upon omega C4 is equal to 0. Why minus n? Because this J goes to the numerator. So
Okay,
then
sir.
I have omega L2 R4 is equal to R2 upon omega C4. So I get omega L2 upon R2 is equal to 1 upon omega C4 into R4. So my quality factor is equal to omega L2 upon R2. That is equal to 1 upon omega C4 into R4. That is 1 upon my dissipation factor. That is equal to 1 upon 0.16. So my quality factor comes out to be 6.25. Okay. 0.16 inverse.
Okay, sir.
6.25. Correct. Okay, so there was a mistake I made. The note also was wrong. So I modified it and corrected it. And then DM got the answer.
Okay, sir. Okay, sir. Okay, sir.
Okay. So let us do a recap. So we considered what is an inductor, what is a resist when there's a resistance added. What are the equations that comes? How one part is a reactance, another part is my resistance. What is the angle of Z in this case? It is 90 degree. The angle of Z in this case varies from 0 to 90 degree, right? There's an ideal capacitor, which is ideal. There's a practical capacitor where there's certain leakage, and that is modeled by a resistance in parallel to your capacitor. This is the impedance, and this is the admittance. So parallel RC is easier to write the admittance. Okay? It is easier to write the admittance for parallel RC. Now, practical inductor, we consider how Q factor is given by omega Ls upon R. So my L should be as high as possible, my resistance should be as low as possible. Then my inductor is as close to the ideal condition. So the quality of the inductor is good. Now the capacitance, the badness factor, dissipation factor is 1 upon Rp omega Cp. And then we also found that D can be written as Rs into omega Cs. We derived this. Okay. Now these AC bridges are used for impedance measurement as well as they can be used for frequency measurement. We also saw a sum for that. At balance condition, Z1 into Z4 is equal to Z2 into Z3. And this frequency measurement only for the sine wave. It is not possible for any wave. These AC bridges are also valid only for the sine wave. It is not possible for any other periodic wave because, as we saw, any periodic wave is composed of sine waves of multiple frequencies. Frequencies are different, sine waves are different frequencies. Okay, so it's not always possible. So this is how we, Z1 is a phasor. It has a magnitude and an angle. And balance condition, what should happen? Both the magnitude should be satisfied and the angle should be satisfied. Then we say that the bridge is balanced. Then we found out what is the angle theta. How do we represent this? Is the phasor diagram. It's exactly not a phasor diagram. In this case, it is the impedance diagram. Okay. Now a parallel LP-RP, we derived a condition for this. So how we wrote the real part, imaginary part, how we get the angle. Then for RLC circuit, how the angle changes. If it is inductive, the angle is 0 to 90 degree. If it is capacitive, it is 0 to minus 90 degree. At resonance, the angle is 0. Then we solved this bridge. It was a ratio bridge. We found this bridge can be used to measure frequency. Okay. And then we found that it can be used only for a sine wave. It cannot be used for any other wave because of the concept of Fourier series. Then we studied Schering bridge, which is used to measure high voltage capacitors. We found a balance condition. So we found the balance condition. We found these were the formulas. Then the equivalence between the series and parallel, we derived it. And we found the dissipation factor is given like this. This is very important. And then how we want this voltage to be low, but this voltage should be high so that it can measure the capacitance. And this for the safety of the operator. Okay, both should be satisfied. We should consider practical case. We want the high voltage to be applied across the capacitor to test it, as well as we want it to be safe for the operator who's conducting the testing. Okay. So both have to be satisfied, and this Schering bridge can help us to do that. It is also a product bridge. And then we consider the power factor for coil. Coil means inductor. This is important. And then we found a quality factor of the coil. So we didn't know R, we didn't have to find LS. And we cannot find also. We cannot find what is RS, LS. Individually, we cannot find. But through the computation of the angle, we could find the ratio. And then we could find the quality factor. Okay. So what does this tell you? Okay, if the power factor is low, then the quality factor is high. If the power factor is high, the quality factor will be low. Okay. Now we consider another case, another bridge we considered, which is again a product bridge. And I made a mistake, so we corrected it. We found the balance condition. And then we were able to find a quality factor. Okay.
Oops.
Okay, so are there any doubts which you have anywhere?
मान लिया कि कैपेसिटर और रेजिस्टेंस मान एक सीरीज में रहा तो उसको फिर पैरेलल में वो ये इक्विवेलेंट ये करना पड़ेगा क्या?
कौन सा
कंपेयर करना पड़ेगा
मानो एक
रेजिस्टेंस और आपका कैपेसिटर सीरीज में रहा, ठीक है,
हाँ
और हम लोग को निकालना है डिसिपेशन फैक्टर, उसको फिर कंपेयर करना पड़ेगा इसके साथ।
नहीं, डिसिपेशन फैक्टर निकालना है तो डायरेक्टली ओमेगा सी एस इंटू आर एस डाल दो, ये हम लोग ने डिराइव कर दिया ना।
अच्छा, डायरेक्ट फॉर्मूला से हम ये कर सकते हैं ना सर,
हाँ हाँ,
निकाल
डायरेक्ट
सकते हैं,
डायरेक्ट हाँ हाँ।
निकालने की जरूरत नहीं है दोबारा से।
नहीं नहीं नहीं।
ठीक, ओके सर।
हम्म,
या इस केस पे भी मान ली कि इंडक्टर और रेजिस्टेंस पैरेलल में रहा।
अगर आर पी और एल पी रहेगा तो आपका क्वालिटी फैक्टर उस टाइम आपका हो जाता है आर पी अपॉन ओमेगा एल पी।
ये हमेशा के लिए ही रहेगा ना सर फॉर्मूला जो है।
और वो है ओमेगा एल एस अपॉन आर एस। ठीक है।
यस सर। ठीक
हम्म।
है। ओके।
हम्म, ठीक है।
ओके सर।
थैंक यू। बाय।
थैंक यू सर। गुड नाइट, गुड नाइट सर।
गुड नाइट। बाय।